Okay. Good afternoon, everyone, and welcome to Improving's Virtual Lunch and Learn. Before we start, please make note of the question mark icon at the upper right corner of the presentation screen. Clicking that icon will open the question and answer feature, which allow you to send questions to be delivered to our presenter at the appropriate time. We are excited to present Michael Perry, Technical Director at Improving, who will be sharing Git as a blockchain.
Thank you very much, Will. Hi, I'm Michael Perry, a technical director based out of the Dallas office of Improving, and I would like to share with you today a cautionary tale. It's a tale of friends and a tale of lunch, a tale of deceit, but most importantly, it's a tale of trust. So I present Git as blockchain. We have a series of friends that like to enjoy lunch together. They all work at a technology company, and so they like to share ideas about different tools, solve different problems, and learn about the tricks of the day. And at lunch, they have friendly conversation. I want to introduce you to the people in our story. At the top left there, we have Daniel. Daniel is very clever and also very opportunistic. And then just below Daniel in the red shirt, we have David. David is an organizer and he's extremely helpful. And then at the top right, we have Thomas. Thomas is very eager to please. Always has a great solution to a problem. And then on the bottom there, we have Tim. Tim is supportive and he's a tool maker. He likes to actually build the best solution to a problem. And so as they're enjoying lunch and they're enjoying their friendly conversation, they have a problem. A problem arises to decide who is going to pick up the check. So Tim says, I believe that it's my turn, but Daniel says, wait, no, you picked up that big steak dinner. It's going to be my turn today. And of course, at no point do they decide to just split the check. No, one person has to pay for it. So they have to figure out how are they going to decide. David has a plan. He says, I'll keep a ledger. And with this ledger, we'll be able to figure out who has picked up the check in the past and who should be picking it up now. So within this ledger, I'll keep track of transfers. So the transfers include the date, the restaurant, everybody who was at the restaurant, and then who actually picked up the check, as well as that check total. And so these transfers represent transfers into and out of the system. It's value flowing from and flowing to the system. So we've got here David is deriving value from the system by ordering a lunch for $13.45. Daniel is deriving some value from the system, but he's also providing value to the system by picking up the check total of $53.97. So as long as the total of the transfers from and the total transfers to are the same number, everything balances, and we've kept track of the lunch. And so now Thomas asks, okay, that's a good system, but how does that help us decide who's going to pick up the next check? And so David says, oh, I've got that figured out too. We can figure out everybody's personal balance. So we take each of the different lunches that the people have been to. We add up the transfers from and the transfers to, and that shows their personal balance, how much value they have derived from the system in total. And so now you just take a look at the personal balance, and whoever has the lowest personal balance, it's their turn to pick up the check. Hey, okay, that sounds like a great idea, except Thomas says, wait a minute. What about all these negative numbers? I mean, I'm no accountant, but I do know that accountants don't like negative numbers. And I think the reason why is that if we buy lunch for people, but then they leave the system. Now they owe the system some money, but they've left. How are we going to reclaim that value? So David thinks about it, says, okay, I think I've got a solution to that. We will buy into a bank. So now everybody, when they start coming to lunch with us, they'll buy into the bank for $40. And then now we can add up the transfers from and the transfers to with that initial buy-in, and everybody's got a positive balance. That way, if they leave the system, now they can just withdraw their remaining balance from the bank and everybody's clear. Okay, I think this will work. And so under this new system, everybody keeps going to lunch, and as long as they have David there with his trusty ledger, they can figure out who needs to pick up the check. So time passes and the company grows. And as the company grows, more people enter our story. Right there in the center, we have Vaughn. Vaughn is extremely creative. He always comes up with some really interesting ideas to solve problems. At the top there, we have Corey. Corey is really smart, and she can always figure out a brilliant solution to a problem, especially when it has to do with Git. You want to know how Git works inside and out? Corey knows. And then at the bottom there, we have Harold. Now, Harold, we would say he's a well-intentioned troublemaker. He's a hacker. He likes to figure out the system. He likes to game things, see what he can get away with. He's not trying to be mean about it. He just wants to play around. So as they're joining the company, we find that now we have more people going to lunch, and we have more groups that are going at the same time. And David can't be with all of those groups. So we have to figure out how we're going to take this ledger and share it among all of the people. And so Daniel grabs a copy of the ledger from David, and he starts to write down his own version of it. And then Vaughn, he grabs the ledger and he starts making a copy. And so now we've gone from having a single ledger to having a shared distributed ledger. And as long as people are copying from the ledger in the afternoon after lunch, then everything is going to stay up to date. So we now have 3 versions of the ledger, and in the afternoon, Daniel copies from David, Vaughn copies from Daniel, and David copies from Vaughn, and everything gets synced up. And then as we have more people joining the system, they copy transactions from somebody, and somebody else copies from them. And we eventually get to this network of, in the afternoon, everybody copying transactions from everybody else. And we've got several different copies of this distributed ledger to use during lunch, but that's a little bit of work to keep things up to date. And so Thomas starts to look at this and says, this looks very familiar. We already have a tool that does this. How about let's use Git? Brilliant idea. All right, so of course everybody brings their laptops to lunch, so they just pop their laptops open and they start creating a repository. And so the first thing that Thomas does is he creates lunches.txt. So this is a text file that contains all the information that was in the written ledger, starting with the buy-ins. So all these folks bought in for $40, and now here is the bank's initial balance of a liability of $240. So the bank owes back that money that was bought in, and that balances that first transaction. And then you've got transfers for each of the different restaurants and the different groups, and all of those balance as well. And that's just one text file, and Thomas adds that to the repository, and then everybody else attaches to Thomas's laptop as a remote and pulls that text file. Okay, so we've got a ledger now that we can share using Git. And so now Tim decides that he wants to automate this a little bit. and he wants to make sure that all of those transfers balance, that all of the transfers in are equal to the transfers out. And so he creates validate.js. And validate.js runs over lunches.txt and adds up all of the transfers, makes sure that everything balances, and then prints out OK. If there's a problem, it'll print out an error message. Hey, this is a great idea. So then Daniel decides that he is going to create another JavaScript file. He will call this one balance.js. So when you run balance.js in Node over the lunches.txt file, you can give it the name of a person, and then it will find all of the transfers with that person's name. And then it will add up all of the transfers in, transfers out, give you their total balance. And that way, at the beginning of lunch, you can say, well, who's at the table? All right, we've got Thomas, Tim, and Corey, and Vaughn, and you node balance each one of those names. You get their total balance. Pick the lowest balance, and you say, all right, it's your turn to pick up lunch. And the system is working great. At the end of lunch, you just append to lunches.txt, check it in, and now in the afternoon, you can just pull from all your peers. So everybody, instead of copying the ledger manually, they can just connect to other machines as remotes and do a git pull. And then that merges all of the changes to lunches.txt, and then they can each validate and make sure that those changes were good. Now, of course, at this point, Corey is saying, you know, we can automate things just a little bit. You're running this validate script every time you pull. Why don't I help you to remember to run that every time you do that pull? So I'm going to create a git hook. And so this git hook is just a shell script that runs post merge. So after you do that fetch and then it's merged into your current branch, then it's going to automatically run node validate over lunches.txt. Now, this isn't going to fail the merge. It's just simply going to print out a result. It's going to say OK, or it's going to say that there is a validation error. But at the very least, you don't have to remember to run validate.txt. And now everybody has the same contract, the same piece of code that you can run on your own machine to make sure that everything is good. So that's a pretty smart way to encode a contract, right? So I would say this is a pretty smart contract. And everybody is running their own copy of it. But then problems start to happen. You see, when you pull from two different people who have been to lunch, they might have so they've each appended their lunch to lunches.txt. You've got a choice to make. You can either pull the left before the right or the right before the left. So some people are going to choose to do left before right, and then other people will choose right before left in order to resolve that merge. And so that resolves the merge locally, but then now you've got two people who have merged in two different ways. When they pull from one another, you get merges of merges. So you get this meta conflict that's happening here. And now it's hard to figure out, well, is it supposed to be on the top or on the bottom? And what it doesn't really matter. They both happen at the same day. So we'll just we'll pick one and keep going. Unfortunately, somebody else might choose to resolve the meta merge differently. And so you get this merges of merges in this never-ending chain of merges that just will never converge. It would be really nice if we could guarantee that eventually everything would be consistent. But the system that we've designed so far does not guarantee that consistency is eventual. So that might be a good property for your distributed system to have. But so we've got this problem of all of these merges of meta conflicts, and it's really because we're putting everything at the bottom of the same file. And so Thomas comes up with another idea. He says, okay, how about instead of a single file, we break this apart into multiple different files. So each file will name with the date and the restaurant, and it will just have the transfers for that particular transaction. And so now we can validate that text file, and we know that that one balances because all the negatives match up with all the positives. And furthermore, since it's not a changing text file that we're appending to, we're not going to get any merge conflicts. And there's a really important reason for that, and that it's that immutable files have no merge conflicts. Well, of course, I mean, because every copy is exactly the same as every other copy, so how could there be a conflict? So maybe it's going to be important for us to build our solutions based on immutable data structures. That might resolve that problem. Okay, so now Thomas breaks apart all of the different transfers that are in the lunches.txt, and we've got a separate immutable file for each transfer. And now Tim updates his validate node application so that it is taking the names of all of those text files, and it's validating each one of them to make sure that they balance. So of course you don't have to send it everything, you just send it the new ones, the things that were created. And then it validates the balances to make sure that nobody has gone negative. And as long as those two checks pass, it prints out OK. But if there is an error, it'll print out an error message. And now that means that Corey has an opportunity to update the Git script, the Git hook. So she does a bit of research and she finds a way in this Git hook to look for differences that are M or D, modification or deletion. And so if you see any of those are your changed files, and you want to prevent people from changing files. You should only be able to insert new files. So then if that list is not empty, then you print out reject the commit in nice red text so that everybody knows to pay attention to it. And then if everything is good, then it prints out only the new files. So it takes a diff and it says, okay, these are the things that have changed. We know that they're not modifications. We know they're not deletions. So therefore, these are inserts. And so now it's validating just the new files. So a bit more complicated Git hook, but now this is enforcing the idea of immutability. This is saying that we cannot change history. We can only create new objects in history. No changing a large lunches.txt. It's only inserting new individual files. Okay, so looks like we have solved a lot of our problems here. So we've gone from a ledger to now a shared distributed ledger to now an immutable distributed ledger. And this seems to be taking care of keeping track of who has picked up lunch in the past and whose turn it is now. And everything's going well until Harold gets an idea. Harold realizes that his balance is getting kind of low. So he can see, well, $7.13. I can't really afford to eat a full lunch on just that money, but and I don't really have the funds to pick up the check for everybody right now. What if I decide that this morning or the early lunch, I'm going to join in on the group that goes to BJ's. They usually leave at about 11:30. And then there, I'll just get a salad. And then The late lunch crowd, they leave about 12:30, and they usually head to McAllister's, and there I'll get a soup. Okay, so he decides that, yeah, that will work. In each case, I will have enough funds to eat half of a meal, but at the end of the day, I've had a full meal and I haven't blown my budget. Okay, I think this is going to work. And so he goes to lunch. They check the balance. Yep, he's not gone zero. It validates. Then he comes back later, goes to McAllister's. They enter that transfer, and it hasn't gone to zero. But of course, then in the afternoon, we've got Thomas and David trying to pull from one another. So they are both trying to merge those two repositories and run the validation over them. Sure, each of the individual transfers validates, but the balances, the balances don't work because Harold's balance is negative $5.08. So they each get the message to reject the commit. So now then they look at each other and say, well, Harold's balance went negative. How did that happen? And so they go to Harold and say, Harold, what are you doing, man? You went to lunch twice here, and now you made your balance negative. And Harold says, well, you know what? I'm just playing by the rules. We set up the system, validates at lunchtime. Everything's cool, right? And they say, well, no, that's not what we intended for it to do. You just kind of gamed the system. And he said, well, if you want to prevent people from gaming the system, you should probably make a better system. So they think about it. Okay, yeah, you're right. So what if we don't allow merges, and we have to have a linear history? If we do that, then there won't be this double spending problem. Somebody can't take their funds and spend them on one version of history and then spend those same funds on a different version of history. Instead, everything has to be serialized. Everything has to be in sequence. Okay, so let's try that. How are we going to make sure that we don't have merges and we do have a linear history? How do we decide between David's branch and Daniel's branch? One of them has to be true, the other one can't be. And then furthermore, what do we do with the one that is not true? What do we do with the loser of this choice? So Corey thinks about this for a while, and Corey says, okay, I have a solution. We'll vote. The way that we're going to vote is you just simply create a new commit on top of that branch. And now the branch that has the most commits is the one that has the most votes. It's the winner. It's the truth. The other branch never happened. Oh, you know what? That's pretty brilliant. That's simple. Yeah, of course. Okay, so if you think that something is the truth, you just go ahead and keep building on that branch, ignore the other one. Oh, wait a minute, but now there's transfers in that other branch that somebody actually got lunch, somebody actually spent money. Those transfers need to somehow make it back into this branch, right? And Corey says, well, yeah, but Git has that covered. Cherry pick. So all you need to do is cherry pick one commit from the losing branch, validate it. Has that caused the balance to go negative? No? Okay. Well, let's keep that one in, cherry pick another one. As soon as you find one that doesn't cherry pick, oh, okay, you can't push that commit. You have to revert that one. Have to reset that one. But now you have to talk to the person that's got the negative balance and work that out outside of the system. We don't have a solution within the system because there is no arbitrator. This is all just done based on our mutual experience with one another, and we're being completely distributed here. So, okay, well, a little bit uneasy about not having an arbitrator, but you know what? That's kind of the world that we live in, right? Maybe that's not a bug. Maybe that's a feature. Maybe rather than a system that relies upon having somebody that can always make the final decision. This is a truly distributed system, and the group as a whole makes the decision. So, okay, yeah, I think we can go with that. Yeah, so if Harold gets up to his shenanigans again and he creates a branch that can't be validated, we're just going to have to talk to Harold and get him to pick up a later lunch, and then we'll rebalance the system that way. Okay, so now we have this linear history of this chain of commits that are all linked together, each one a block of transfers. So we're starting to create a data structure that that might really solve this double spending problem. And of course, then Daniel sees an opportunity. He says, you know what? All I have to do is go into this block of transfers and I can change my name to David's name. Yeah, not a problem. And so now David's balance gets deducted, but mine doesn't. And so that means that I can eat for free. Let's give this a try. And in order to cover my tracks, what I need to do is make sure that when I commit this, so of course I have to be the one to handle this transaction in order for that to work. And when I commit it, I'll just make sure that the author is David. There we go. So now we've faked out the author, we've faked out the transaction, and it gets into the system. And then eventually David realizes, you know what, my balance is supposed to be a little bit higher. And he gets to looking through the history because the history is all there. It's a shared public ledger made out of immutable blocks of information. And you can see this entire history. And he says, oh, wait a minute, I didn't go to McAllister's that day. What happened here? So he asks around at the other people that are listed in that transfer and says, well, were you there? Do you remember who else was there? And well, no, that was so long ago. I don't really recall. And so Daniel gets away with it. But everybody's suspicious. Everybody's looking over each other's shoulders and trying to figure out who changed the ledger, who put a transfer in there that that wasn't valid. But then Tim always comes up with the great tool solution, and he says there is a tool for this problem, and it's called a public key. So he pops open OpenSSL and he generates an RSA key, and he saves that to his own laptop. And then meanwhile, he copies the public key from that RSA key pair, and he puts that into the repository. So now everybody can see his public key, but he's got the private key and the key pair stored away on his machine. Okay, we kind of see where you're headed. Now let's finish this out. How are you going to use this in order to protect the history and make sure that nobody tampers with things? He said, well, okay. So what I'm going to do is I am going to start signing all of the transfers that I take care of with my private key. And furthermore, I'm going to start using my public key as my identity. Okay, well, there's your public key. Wow, that's a lot of information. That is 4,098 bits of information. I can't remember that much information, sorry. We're going to have to make that more compact. This is okay, well, I can just run a SHA-256 hash over that. That's still 256 bits of information. Nope, got to be shorter. Okay, let's just take the first 7 characters of that. All right, so that first 7 characters, we'll call that the fingerprint of the public key. So if somebody were to change their public key, they would get a new hash and they would get a new prefix for that hash, so a new fingerprint. So this fingerprint basically stands in for an individual. It says, okay, so now that is something that we can glance at and say, okay, CC7OB2D, that must be Tim. Okay, and so now everybody creates their own key pair, puts their public key into the repository under the fingerprint.pub file name. And so now everybody, after they do a pull from one another, has everybody else's public keys. Okay, that's great. So now we can take that public key file, we can run the hash because we have that capability on our machines, and we can check that prefix, and we know that that fingerprint matches the public key that's in that file. So we can validate these public keys based on their fingerprints. Okay, this is starting to help out. Now there's one more thing that we need to do, and that is every time we create a file that represents a bunch of transfers, rather than using our names, we're just going to use the fingerprints of our public keys. Those will be our identities. Okay, so you mean we're kind of being anonymous? Well, we're not entirely anonymous because, you know, if I go to lunch, then you need to know what my fingerprint is so that you can put that transfer together. So it's not totally anonymous, it's pseudo-anonymous. So we've got this pseudonymous identification scheme sneaking into the solution. Okay, well now so we've got a public key associated with each individual, and so that means that now we can sign these transactions. Okay, that sounds great. So what we're going to do is use OpenSSL to compute the digest of the lunch file. So we have all the transfers, and then everybody that was at lunch that day takes that digest, and they produce a signature using their own private key. And now they take those signatures and they put them into the repository. And now all we need to do is, using OpenSSL, we can recompute the digest of that lunch file, but then now compare the signature with using the public key of the person that signed it. And so now we can validate everybody's signatures. So that means if the text file says that Tim was at lunch, and then we can look up Tim's public key, we can validate that Tim signed it. So now we can't have somebody going in there and changing their name to somebody else's. They wouldn't be able to produce a valid signature because they don't have that other person's private key. Wow, it's so simple. All we have to do is check all of those signatures in next to the lunch text file, next to everybody's public keys, and then we run all those validations and everything works. Brilliant. Wow, that's a lot of validation. Okay, Tim says I can update the validate JS. So it validates all the public keys using the signatures. It validates the signatures using the people that were listed at that lunch. Validates the balances. Make sure that everything balances out and that nobody has gone below 0, and then it prints out OK. Whew! Wow. That's a lot of work, but hey, we automated some of it and it solves the problem. So now everybody has digitally signed the transfers in this record. So now it's not just a ledger, it's not just a distributed ledger. It's not just an immutable distributed ledger. This is a cryptographically protected immutable distributed ledger, a sequence of blocks going back through history in order to record this public record of everything that happened. Hey, I think we have built something here. I think this could really catch on. So the final step of it is that we need to be able to compute somebody's balance, but we don't have their name anymore because our system is pseudonymous. So so that means Thomas goes in and he updates the balance.js to take the fingerprint and uses that instead of the name, and everything is working out. But then Daniel sees another opportunity. He says, you know what? there's a lot of work that has to go into keeping track of a lunch, and not everybody really wants to take on that work. So some people aren't bringing their laptops to lunch. Some people aren't pulling in the afternoon. They're just letting somebody else take care of it. I will be that person. I will take care of things for you, but it's going to cost you. So he announces to everybody, okay, when you go to lunch, I'll take care of it for you. All you need to do is tack on a little transaction fee. So you buy your lunch and then you tack on 5 cents. Now, of course, this transfer isn't going to balance anymore because it has 5 cents missing from everybody who participated in lunch. So we've got 5 people here. That means we are short 25 cents. Well, I'm going to add another transfer before I commit this, where I'm using my own private key. So I am digitally signing this, and I will take that 25 cents and I will withdraw that information, that value from the system. Meanwhile, we also have this bank that's growing over here, and that money's not going anywhere. It's not doing anything. I'll take $1 from the bank too. And so with the transaction fees and with this this data that I'm mining from the value of the system, then I can pay for the work that I'm doing on your behalf. Does that sound like a great idea to you? And Vaughn says, wait, hold on a second. Now, I agree that somebody needs to take on this work, but I don't think that it's just you. I think I'm going to go ahead and compete. And he tells everybody, if you use me instead of Daniel, then you just need to put in 3 cents. And Daniel says, well, okay, that's fine, but it's going to cost you just as much to run the servers in Azure that it does me. So, the value that you get out of the system and the cost of running it are going to start to balance out anyway. We'll find the right point. So sure, let's compete. And so they start to both handle the transfers and both derive some of the value from the system. So every time they add a new block to this chain of history, they get a little cut. They get a little piece. They mine a little bit of value in each one. But then Harold gets an idea. Says, there's value being generated every time somebody handles something in this system. Doesn't really need to be a lunch for that to happen. So the next day, people go to work and they pull and they see in the repository there's a whole bunch of new transfers in there. They say, wait a minute, those don't look like lunches. I think there's something fishy going on here. And so they take a look inside of those files and they see all that Harold's doing there is he's creating these little tiny transfers that just move money back and forth between 2 public keys. And then with each one, he's appending, as according to the rules, a new transfer that withdraws some money from the bank. Now, he's not collecting any transfer or any transaction fees. Why would he need to? But what they do notice is that, hey, wait a minute, you've got 2 fingerprints here. How did you do that? Oh, well, fingerprint is just you stand in for a public key. I can generate 2 of those. There's no rule that says that 1 person, 1 key. In fact, I can generate as many as I want to. If I want to move money from one wallet to the next, yeah, who's to stop me? Oh, you know what, wallets, that's a pretty powerful idea. So that means that, yeah, the public key doesn't represent me. The public key represents this wallet. And then by virtue of the fact that I own the private key, I control the wallet. But okay, so I can use different wallets for different purposes, and I can have some that are transferring funds really quickly. Those can be my hot wallets, and then I can have some where I move the money back in there and I keep them cold. Oh, but I'm getting ahead of myself. We're just trying to solve this problem here. And hey, Harold, you're gaming the system again. Stop that. He says, well, how are you going to stop me from creating these bogus transactions where I'm just moving money back and forth and taking a little bit from the bank each time I do? And so Corey thinks about that and she says, I have an idea. So she grabs her laptop and she creates a commit. And then just as she's typing in the commit message, she slams her fist down on the keyboard. Bam! She looks at it, says, nope, that's not right. Reset. Creates another commit. Bam! Reset. Let's try one more commit. Bam! Yes, I got one. And she flips her laptop around and she shows everybody, look, I got one. What did you get? I'm not seeing it. Well, look at the commit hash. 0C2756C. Okay, that's a commit hash. That first digit, it's a 0. Oh, okay. Yeah, first digit's a 0. It could have been 0 through F. It could have been any one of those 16 values, but I kept working at it until I got a 0. And that 0 right there, that is proof that I did that work. Well, we saw you do the work. We saw you slamming that keyboard. Yeah, but you don't need to have seen the actual work. I mean, actually, I was resetting back to the head, and then I was adding the next commit, coming up with a random commit message, and then seeing what the hash ended up being. And so, nope, that one starts with A. Let's reset it. Let's do another random commit message. Okay, so that's the actual work that you did. And the proof that I have is that the commit starts with a 0. Okay, so you mean we don't have to have actually seen you do the work. We have that proof of work in the hash itself. That's right. Okay, so that kind of slowed you down. It took you a little bit of time to do that work. Yeah, I got lucky, and this time it only took me 3 times. But if you think about it randomly, it should have taken me on the order of 8, half of the 16 possible values in order to get a 0. Okay, so that means that we now know roughly how much work you had to have done in order to accomplish that. So how does that help? Well, you see, this will slow Harold down, and he can't create quite so many bogus transactions. And Thomas says, well, you know what? Hang on, I can write a script. I can do that work faster. So he just writes a little Node application called mine.js, and he passes in -target8. And so it keeps on performing that operation, creating these random commit messages. And every time it comes up with a commit hash, it prints it out and it says, aha, look there. I've got a commit with 2 zeros at the beginning. I targeted 8 bits, and so now I've got a full byte worth of zeros. It took me 215 attempts to get there. So I mean, I was really pushing that maximum expected value of 256. Usually it would happen about halfway there. But yeah, I see what you mean. So everybody can run this script, everybody can mine, but it's going to take, on average, 128 attempts for somebody to come up with a commit that starts with 2 zeros. And if we need more time, if we have more computing power, and more people are trying to add to the chain of blocks, we just demand more zeros. We just increase the difficulty. We require more proof. Okay. Yeah, so they put their proof of work system in place, and now they've got these random commit messages, and all of the commits begin with 2 zeros. So it takes a while to create each one. And meanwhile, everybody is taking the longest chain. So if somebody else comes up with a commit that has 2 zeros, it might take them a little bit of time to build on top of that. Meanwhile, the longest chain will continue to grow. So this means that we end up building a linear history, and we do it in such a way that not one person can own that history. Harold can't go in there and just start creating commit after commit after commit. Okay, So yeah, I think we've locked you out, Harold. I think we got you figured out this time. Yeah, not so fast. Not so fast. Yeah, Harold, he gets another idea. He says, you know what, Thomas, that was a great script. But if we were to join forces, then we could outcompete everybody else. Here, let me tell you what I'm thinking. So we are going to each run our own mining rigs, and we're going to try to find the next block in the chain. When we do, we are going to build on each other's blocks. We won't build on somebody else's blocks. So if we see that Vaughn has committed something, ignore his. Go back to yours in the past. I'll try to build on top of yours. You'll try to build on top of yours. Okay, and then you found another one. There you go. We'll start building on top of that one, and we'll kind of lock Vaughn out. So as long as we join forces, we can outcompete. We can outcompute everybody else. Okay, so they each set up their own mining rigs. Harold's got one. Thomas has got one. Meanwhile, Vaughn said that he was going to compete. Daniel has gotten into the competition game. And so now anytime Daniel or Vaughn adds something to the history, Harold and Thomas just kind of ignore it and try to build around it. And we're on pretty even ground here. Harold and Thomas have about half the computing power. So it's pretty neck and neck. But you know what? Harold just kind of spins up another server real quiet like, and he starts now Harold and Thomas as a conglomerate have more than half of the computing power, and so now they can start building those longer chains, and then the others will struggle to keep up. So as long as they have more than 50% of the computing power, they can be in charge of the network, and then they can decide whose transfers get in and who gets those delicious transaction fees and who withdraws that money from the bank. But then the others realize what Harold and Thomas are up to, and so Daniel spins up another one. Okay, we're back to 50%. Well, now Thomas has to spin up a new machine. Okay, well then Corey gets into the mix, and she says, okay, I'm going to compete as well on a level playing field, not favoring anybody's over anybody else's. But that still means that Harold and Thomas only have 50%. So Harold spins up another machine and then another one just to make sure that things are safe. Yeah, Thomas is starting to spin up machines. David comes in and starts to create nodes on the network. And then people are just creating new and new machines in order to make sure that nobody can gain more than 50% of the computing power. Also that they can prevent somebody from writing all the history that they want to write, locking everybody else out, and taking all of the transaction fees and mining all of the value out of the system. So things escalate, chaos ensues. What we used to have here is a group of friends who are going to lunch in order to have friendly conversation, trying to solve the problem of who's going to pick up the check. And it has devolved into this system of distrust and deceit and everybody trying to outdo everybody else. Along the way, we've come up with some really good solutions. We've solved some really tough problems. So we took this idea of a ledger and we shared it so that everybody can make the best informed decision. We shared that ledger using Git so people can peer-to-peer consolidate with one another. We put the validation in there so everybody is running that smart contract on their own. Now rather than having things that are based on somebody's name, it's pseudonymous. It's based on public keys, so they can be signed and those signatures cannot be forged. So through all of this, we've got these immutable records that are carried forward in this linear history of non-merging chain of commits. And so we've protected against this 51% attack by having this proof of work that that demands more and more proof and more work as more people join the system. So all of these solutions in and of themselves are great ways of solving the problem, but they all miss something really important, and that is trust. We started out with a group of people who trusted each other, and now we've built a system that demands zero trust. That I mean, yes, that's a feature. It works without trust, but that's also a bug. That means that the only way in which it does work is by assuming that people are untrustworthy. So if we were to re-inject trust into the system, we wouldn't have to have just blind trust, just everybody's going to do the right thing and everybody's going to play by the intended rules. No, not blind trust, but a trust based on working with somebody over time, a trust based on a shared history, and a trust based on the assumption that that person is going to get value out of that relationship in the future. So if you build these trusted relationships and you build these organizations where the value of being a member of the organization is far more than any value you could extract from a one-time hack of the system, then you can have smart trust built into the system. Once you have smart trust, some of these solutions no longer need to apply. You no longer need to have that proof of work, because now it's just knowing that you are part of this organization is going to prevent you from doing something that is going to get you a small gain right now, but lose you a valued relationship in the future. Not having that proof of work means that it's no longer based on compute power, and you're no longer just burning up electricity in order to make sure that this thing stays running, and so you don't have to worry about that 51% attack. Most importantly, you don't have to worry about having a linear, non-merging history. If you allow for people to be autonomous and to make their own decisions, and you trust that they're going to do so in a way that ultimately benefits them more because they're part of this trusted organization, then you can allow them to make that change independently and merge their history later. And this is the way that open source works, right? This is the way that Git works. So why not take that and bring that into the system? Now, of course, the problem that Git solves in open source is one that's based on a trusted relationship. The problem that blockchain solves in finance is about preventing double spending, and it's an adversarial relationship. It's a zero-sum game. So when choosing a solution for a problem that you have, think about, do I have trusted organizations? Do I have these groups that will allow me to use all of the power of this merging history of immutable commits that I have in Git? Or do I have a zero-sum game where I have to prevent somebody from double spending a coin? And if that's my problem, okay, a blockchain is your solution. But so many times, that's not the problem that we're trying to solve. The problem that we're trying to solve is just having a public ledger, having information that you can verify that is out there and that is shared. That's the open source problem. That's the problem that something like Git can help solve. And so I think that kind of the takeaway from this is, let's look not to blockchains to solve these problems, but let's look for immutable data structures that, based on trusted relationships, can help solve better problems and help solve them in a more scalable and achievable way. I outlined some of these solutions in my brand new book, The Art of Immutable Architecture. You can find out about it at immutablearchitecture.com. And I have been Michael Perry, and thank you so much. Back to you, Will.
Great, thanks, Michael. So We don't have any questions that have been posted. I will wait just a few seconds to see if any come in. Often that happens at the very end. People like to forget about it. But in the meantime, can you tell me just like what is that tie-in right there for immutable architecture that you really pushed that, you really like that, and it even came up here in the blockchain. Do you think that's going to help us?
Oh yeah, yeah. So if we take a look at some of the architectures that we are currently relying upon, Git is a great example of an immutable architecture where the commits themselves are immutable because they're identified by hash. If you were to change the contents of the commit, you changed the hash, you changed its identity. It's a different commit. What if we were to build our applications with that same kind of architectural constraint? One way that we do that right now is event sourcing. You end up with a history of these immutable events that if you were to replay those events, you could figure out what the current state is. So rather than having state that changes and is really difficult to merge, immutable files have no conflicts. So any copy of an immutable record is just as good as any other copy. So everybody can have the same history of events, and they will come to the same conclusion. So I think the thing to explore, and the thing that I really explore in the book, is maybe it doesn't have to be a linear history like event sourcing or like blockchain. Maybe it can be something that's more divergent and something that allows merges, something more like Git. So those are the immutable data structures that I think we can explore. And one of the great examples that I pull from is something called a CRDT, a conflict-free replicated data type. And this is an immutable data structure that that you can perform operations on different machines, and then when they merge, they will not have any conflicts. The mathematics of the data structure guarantee that.
Okay, great. And we did just get one question that who is buying lunch next time out?
Lunch is on me.
All right, great.
Absolutely. As soon as this this thing is over, buying everybody lunch.
Well, thank you very much, Michael, for sharing. I know I probably am not going to look at Git the same anytime soon. And thank you all for attending Improving's Virtual Lunch and Learn. The recording of the session is going to be available tomorrow from our virtual events page at improving.com/virtual-events. We at Improving hope you enjoy the rest of your afternoon.